Okay, looking at the problems on the worksheet from chapter 13, the first question is about, well, the concept is, I better read it and then say that. A road is made by pouring concrete into 15-foot long segments. The road is built when the air temperature in the shade is 73 degrees Fahrenheit. The highest temperatures in the region are 110 degrees Fahrenheit and the lowest temperatures are minus 4 degrees Fahrenheit. How big do the expansion joints at the end of each segment need to be at the time of construction to keep the road from buckling? What is the largest gap that will exist in this expansion joint as temperature fluctuates? So the first thing you're going to need to do is to identify what the concept is. So the concept here is that it's going to expand when you change temperatures. So that is the concept of thermal expansion. And I know I didn't give myself nearly enough space to write in my answers. So in order to do thermal expansion, we need to first convert temperatures into SI units. These temperatures were given in Fahrenheit. So the SI unit for temperature is kelvins, right? But we can use Celsius here because it's a change in temperature. When you're doing a change in temperature, you can use Celsius or Kelvin and you get the same result. So I'm going to do it to Celsius. So our equation is temperature Celsius is equal to 5/9 temperature Fahrenheit minus 32 degrees. Okay, so my units don't really, the 5/9 is 5 degrees Celsius per Fahrenheit. So using that equation, doing the calculations, you find that minus 40 degrees Fahrenheit is minus 40 degrees Celsius. You might remember in class I said, we physicists think we're so funny. It's minus 40 out. Is that Fahrenheit or Celsius? Ha, 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 ha. 73 degrees Fahrenheit, when we do the calculation, it turns out that is 22.77 repeating degrees Celsius. Granted, we only have 2 significant digits, but I keep all my digits initially and then do significant digits at the end of the calculation. And 110 degrees Fahrenheit is 43.33 repeating degrees Celsius. Now we have to look up the coefficient of, and what is this doing? It's expansion, so coefficient of, and there's no way I can fit thermal expansion in here, so I'm going to put THEXP for thermal expansion of concrete is, and I looked that up, and it averages 10 times 10 to the minus 6 per degree Celsius. Now it averages, it could be between 7 to 12, so we're just going with the average here. So the concrete will, what? Concrete expands when temperature increases. So we need to calculate how much the concrete will expand going from 70 degrees Fahrenheit to, as temperature increases, that would be going to the top one, to 110 degrees Fahrenheit. So I now calculate the so let's calculate that now. So that's going to be change in length equal, that was a very fine change in length, wasn't it? Change in length is equal to the initial length times the coefficient of thermal expansion times the change in temperature. So in our case, that's equal to my original length. Well, the original length was in feet. Well, feet's not a standard metric unit. I don't like to work in non-metric units, so I did a conversion. I don't have the conversion memorized, but I do have this memorized. 15 feet times, there are 12 inches per foot. And there are 2.54 centimeters per inch. And then, of course, I'll have to multiply by 1 meter per 100 centimeters. And so it turns out 15 feet is equal to 4.572 meters. Now, this 2.54 is actually an exact number, so that's the only significant digits issue would be the number of significant digits in my length there. And so my original length is 4.572 meters 10 times 10 to the minus 6 per centimeter or centigrade Celsius degree, and then my change in temperature, which is going to be my 110 degrees Fahrenheit, except for using Celsius, so 43.3 minus my 3 degrees, which is 22.77, and that equals, I'm going to just switch it over to millimeters immediately, 0.9940 millimeters. So the concrete will expand 0.940 millimeters between 73 degrees Fahrenheit, the construction temperature, and 110 degrees Fahrenheit, the highest temperature. So that's how much additional expansion joint there needs to be. So that's going to be 0.94 millimeters to the correct significant digits. Then the second question, what is the largest gap that will exist in this expansion joint as temperature fluctuates? Well, that's going to be the expansion between the maximum and the minimum. So I'm going to put between minus 40 degrees Celsius and, or degrees Fahrenheit is Celsius the same, and 110 degrees Fahrenheit. So I just do the same calculation. Now, okay, I shouldn't have put that. I am a purist. If you use the 15 meters or 15 feet or 4.572 meters, you would get the same answer I'm going to get. But I'm going to put 4.572 meters plus 0.00094 meters. There, I put in the expanded length, my coefficient of thermal expansion. And I get 3.81 millimeters. Now, why do I say I'm a purist here? Instead of using the length that I had for when it was at 73 degrees, I said the maximum length, and then I'm doing the change in length going from its maximum length to its minimum length. So that was my calculation. The difference between maximum and minimum length is 3.81 millimeters, which to two significant digits, 3.8 millimeters. So that's the biggest gap that's going to exist. And the gap that they need to make when they make it is roughly 1 millimeter, or 0.1 millimeter. Excuse me, roughly 1. I was right the first time. Okay, so that was a problem with thermal expansion. The second problem is a problem involving an ideal gas. So since this is an ideal gas, I can use the ideal gas law to relate the two states and find the number of, to relate the two states and to find the number of molecules. So I'm going to do that first. Well, I see molecule, yeah. The second one, Avogadro's number. Can be used to convert between molecules and moles. So let's do the first thing. Let's calculate the number of molecules or number of moles, whichever you prefer. So we know PV equals nRT or PV equals nKT. The difference in the two is just using moles or molecules. So I chose to use in my solution the first form here. And so if you solve that for n, you have n is equal to PV over RT. Well, you need to know what R is. We're given a pressure in units of atmospheres. We're given the volume in units of liters, and we're given a temperature in units of Celsius. We have to convert temperatures to Kelvin. Because this is not a change in temperature but an actual temperature, we must use Kelvin temperatures. So standard temperature is 0 degrees Celsius or 273.15 Kelvin. Standard pressure, as we'll use later in this problem, is 1 atmosphere. And we start this problem at standard temperature of 0 degrees Celsius or 273.15 kelvins. So I'm just going to put in my numbers here. Back to green. My pressure was 0.545 atmospheres. My volume was 2.35 liters. My temperature is 273.15 kelvins. And then my value for R. Now, as I said in class, you will find multiple values for R with different units. So I'm going to look at my units here. I have atmospheres, liters, kelvins. And so I'm going to look for, just looking up in the table, what is the value for the ideal gas constant with atmospheres, liters, and kelvins? And what I find is R is equal to 0.082057 liters times atmospheres divided by moles times kelvins. So that's the number I'm going to put in here. And so my atmospheres will cancel, my liters will cancel, my kelvins will cancel. I'm left with 1 over moles, or moles, and doing the calculation, that gives me, and I already did the calculation, so I'm just looking over at where I did my calculation, 0.05714 moles. Now, of course, to significant digits, that's only going to be 0.0571 moles. I just kept the 4 to have more than the minimum for calculational purposes. So that many moles. Now, if I wanted molecules, I would simply say the number of molecules is equal to the number of moles times Avogadro's number, equal to 0.0571 moles times 6.022. I'm sorry, I don't have it memorized. It's in the 23rd. Molecules per mole. And I actually didn't do that calculation. Let me do that calculation real quickly here. 0.5714. And so that's 3.44 times 10 to the 22 molecules. And the size of this number illustrates why we don't like to use molecules, why we use moles so much. That's a really big number of molecules, whereas the number of moles is small, but is an easy one to write. Okay, so there I use Avogadro's number to convert between molecules and moles. The result of blank derivation can be used to find both the average kinetic energy for molecules and the RMS speed molecules. That's the derivation I did in class that I told you students find annoying, but it's really important because it actually shows you a reason why, and that's the kinetic theory of gases. So from that kinetic theory of gases, we get the relationships that VRMS is equal to the square root of 3 kT over m, where m is the mass per molecule. So if I look up helium, m for helium is equal to, well, the molar mass, which I should put a capital M if I'm going to do molar mass, equals 4.02 grams per mole. And if I convert that by simply using Avogadro's number, dividing by Avogadro's number, and converting to kilograms, I get the molecular mass is 6.64663 times 10 to the minus 27 kilograms. That's the mass of one hydrogen, or helium, excuse me. I did drop to 6. The mass of one helium atom or molecule, since it's monatomic. So the temperatures must be in which units? In kelvins, to use the ideal gas law, or excuse me, to use the well, to use this equation. I can't think right now what I was thinking when I put that. I think I was just repeating the line from above must be in kelvins for the ideal gas law. And so 0 degrees Celsius is 273.15 kelvins. 20 degrees, 293.15 kelvins. So now we're ready to do the calculation for the RMS speed at each case. Also, it asks for the volume if the gas is allowed to move 20 degrees Celsius. I didn't put that here in my shortcuts. I will have to say I forgot. So the RMS at 0 degrees is equal to square root of 3, well, we already wrote the equation, we just put the values in, 3 times K. I have to look up K. K is just a constant, 1.38, what's the rest of my digits? Well, is what we have, I don't have a mistake. 1.38065 times 10 to the minus 23 joules per Kelvin. And so I got that here, 1.38065 times 10 to the minus 23 joules per Kelvin. Times my temperature of 273.15 kelvins, divided by the mass per mole, which was, you can see right there, 6.6463 times 10 to the minus 27 kilograms. Square root that whole thing, and we get 1,305 meters per second. Of course, to correct significant digits, that is again going to be 1,300 meters per second. And the RMS at 20 degrees, same calculation. Now using 293.15 kelvins. And that gives us or to correct significant digits. To correct significant digits, the difference is twice as big. Now, there are two more things that I need to do. One that I skipped over, but I should have done earlier, and that is finding the volume when the temperature increases. And the other is finding the average kinetic energies. So let's do the average kinetic energy to finish this out, and then go back to finding the volume using the ideal gas law. So I can find kinetic energy average two ways. It's 1/2 mv RMS squared. That is, the average kinetic energy is the average of 1/2 mv squared, but VRMS is the square root of the average of v squared. So that is one way of doing it. The other way of doing it is 3/2 kT. It's generally easier to do the 3/2 kT, so I'm going to do it that way. Kinetic energy average at 0 degrees is 3/2 times 1.38065 times 10 to the minus 23 joules per Kelvin times my temperature in kelvins of 273.15 kelvins, and that equals 5.66 times 10 to the minus 21 joules. If you do the 1/2 mv squared, you'll find you get exactly the same value. And switching to the kinetic energy average at 20 degrees, and that gives us 6.07 times 10 to the minus 21 joules. So the molecules are moving relatively quickly, 1,300 meters per second. That is roughly 4 times the speed of sound. That's going pretty fast, right? Why is that faster than the speed of sound? Well, if you think about it, air is basically nitrogen, which has an atomic mass of 28, whereas this was helium with molecular mass of 28. This is helium with a molecular mass of 4. So the difference between nitrogen gas, which is roughly air, and helium for the RMS speed is going to be the square root of 28 over 4. And so 28 over 4 is going to be, 4 goes into 7? Yeah, 7. And so then I take the square root of 7, and that should be roughly the ratio there. Now, the last thing we have to calculate was the volume. So we have P equals nRT. So if I just put subscripts, PV1, nRT1, I didn't put subscript on N because it stays the same. Divide that by P2V2 equals nRT2. The N's and R's are going to cancel. And so I have a simple relationship between pressure, volume, and temperature. This works for any ideal gas, right? And so we were given the original temperature, pressure, and volume, and then we're given the final temperature and pressure. So I'm just looking for that final volume. So solving this for V2, so notice I have the units are going to cancel for everything, so it doesn't matter what my units are. My pressure 1 was 0.545 atmospheres. Pressure 2 is 1.00 atmospheres. My temperature 2 was 293.15 kelvins. You must use kelvins. If you try using Celsius, you get a wildly different answer. That is one that is undefined. It's wildly different. And my volume initial was 2.35 liters. And so when I do that calculation, I find that my final volume is, as luck would have it, I did not calculate this one either, so let's just do that real quick. initial divided by pressure final times temperature final divided by temperature initial, and then time divided by initial. 1.37. There's more digits, but these are the only ones that are significant. Liters. Okay, so there we have done the entire problem. What is the volume if the gas moves to 20 degrees Celsius? Of course, that was 1.37 liters. How many molecules of gas are present? That was 3.44 times 10 to the minus 10 to the plus 23, not minus. You cannot have less than one molecule, or a fraction of a molecule, I should say. You could have a perfect vacuum. It could, in theory, exist. And what are the RMS speed and average kinetic energies of each of them? Well, those we have to refer to numbers in red and black down here because numbers in the boxes. All right, so that's how to do those two problems. Hope you picked up a few things.